Welcome! In this video, we'll explore poles and zeros of transfer functions, fundamental concepts in control systems and signal processing. A transfer function, often denoted g of s, models a linear time-invariant system in the Laplace domain. It's typically represented as a ratio of two polynomials, n of s divided by d of s. The zeros of the transfer function are the roots of the numerator polynomial, n of s. These are the values of s for which the transfer function g of s becomes 0. The poles are the roots of the denominator polynomial, d of s. These are the values of s for which the transfer function g of s becomes infinite. Plotting these poles and zeros on the complex s-plane, where s equals sigma plus j omega, gives us the pole zero diagram. This diagram is incredibly useful for understanding system behavior like stability and frequency response. So, how do we find these poles and zeros? First, express the transfer function g of s in its simplest rational form, factoring the numerator and denominator polynomials. Second, solve n of s equals 0 to find the zeros. Third, solve d of s equals 0 to find the poles. Finally, mark the zeros with circles and poles with crosses on the complex s-plane. The location of the poles is crucial for determining system stability. Poles in the left half-plane, where the real part sigma is less than 0, correspond to stable modes that decay over time. Poles in the right half-plane, where sigma is greater than 0, lead to unstable modes that grow over time. Poles exactly on the imaginary axis, where sigma equals 0, result in marginal stability or instability if repeated. Let's look at our first example. g1 of s equals s plus 2 over s plus 1. The numerator s plus 2 equals 0 gives a 0 at s equals minus 2. The denominator s plus 1 equals 0 gives a pole at s equals minus 1. Plotting this, we place a circle at minus 2 and a cross at minus 1 on the real axis. Since the pole is at minus 1 in the left half plane, this system is stable. Example 2. g2 of s equals s times s plus 3 over s plus 2 times s plus 4. The numerator gives zeros at s equals 0 and s equals minus 3. The denominator gives poles at s equals minus 2 and s equals minus 4. Plotting these, we have circles at 0 and minus 3 and crosses at minus 2 and minus 4. All poles are in the left half plane, so this system is stable. Example 3. g3 of s equals s plus 1 over s plus 2 squared. The numerator gives a 0 at s equals minus 1. The denominator, s plus 2 squared equals 0, gives a repeated pole at s equals minus 2. We say this pole has multiplicity 2. On the plot, we show this with two overlapping crosses or a superscript 2 next to the cross at minus 2. The pole is in the left half plane, so the system is stable. Example 4 involves complex roots. g4 of s equals s squared plus 4s plus 5 over s squared plus 2s plus 2. We use the quadratic formula to find the roots. The numerator s squared plus 4s plus 5 equals 0 gives complex conjugate zeros at s equals minus 2 plus or minus j1. The denominator s squared plus 2s plus 2 equals 0 gives complex conjugate poles at s equals minus 1 plus or minus j1. The plot shows circles at minus 2 plus j and minus 2 minus j and crosses at minus 1 plus j and minus 1 minus j. Notice complex roots always appear in conjugate pairs for systems with real coefficients. Since the real part of the poles is minus 1, which is less than 0, the poles are in the left half plane, and the system is stable. Complex poles indicate oscillatory behavior. To summarize sketching the pole zero diagram, draw the sigma and j omega axes. Mark each finite zero with a circle and each pole with a cross at their complex coordinates. Indicate multiplicity for repeated roots. This visual map is key to understanding system dynamics. Here are a few practice questions. Try finding the poles and zeros for these transfer functions. Pause the video and check your answers. For H1, the zeros are at -1 double, poles at 0 and -5. For H2, zeros at -3 and -6, poles at -1, -4, -7. For H3, no finite zeros, poles at -2 plus or -J3. For H4, zeros at 0 and -1 plus or -J3. A triple pole at -2. Understanding poles and zeros and their representation on the S-plane is crucial for analyzing system stability, designing controllers, and predicting system responses. Thank you for watching.